Okay, so in this lecture, what I want to do is I want to go through the example of a beam structure from page 420 of the reader. Okay, so let's start with a setup, and then it's intentionally done to not complicate things too much. Okay, but it's a four-noded structure, so we have three elements. Okay, all beams. Nodes are labeled 1, 2, 3, and 4, like this. Okay, and then the first one, we're going to cantilever it. Okay, the last node, okay, or the last end, we're also going to cantilever it. Okay. Number 3, we're going to put on a rolling support. Okay, and then we're going to assume, right, that there is an external load, force, applied in a downward direction with magnitude P. Okay. So each element has EA and I, right? It's the Young's modulus, cross-sectional area, and the moment of inertia. EAI, and we're going to keep things symbolic. I, okay. The lengths are given by L, and for simplicity, we'll assume that these guys are equal. Okay. And so now what I want to do is apply what we've developed. Okay, we developed a element stiffness matrix for the beam structure. So now I'm going to combine that, right, together with the sort of structural analysis procedures that we studied, okay, for the trusses, right, and you'll see how they will work in the case of the beam, to sort of completely resolve this structure, okay, the three-element structure, under the applied loading conditions and boundary conditions. Okay. Okay. So first thing first, right? We need to label everything. Okay. So here's our structure again. 4 nodes. Okay. 1, 2, 3, and 4. Okay. So now let's identify and label our boundary conditions. Right, so this guy is cantilevered, and this guy is cantilevered. Okay. So what this means, right, is node 1 and 2 cannot move up or down, right, or there cannot be a rotation at that node, at these two nodes. Okay. Right. The fact that this guy is on a roller, okay, it means that it can rotate, move back and forth, but cannot move up and down. Okay. So with that in mind, okay, and then let's make another observation. Right? So as I mentioned in the previous lecture, the sort of bending action, right, and extensional action, right, through the truss are actually decoupled. Okay, and so for this situation, right, all we're seeing are vertical forces. Okay? And so in principle, we can introduce, horizontal displacement degrees of freedom for this problem, but they're not necessary because they will be exactly 0. Okay? Because there's no explicit forcing acting in these directions. The geometry is completely lined up with the x-coordinate system, right? So there's really no difference between local and global descriptions. Okay? And as a result, all we're going to see is the sort of the parts of the modeling, right? The differential equation will be active. Is that for a beam? Okay? So as a result, right, we can discard horizontal displacements as the degrees of freedom, right? As DOFs, okay? And so this is good because we got rid of 4 DOFs, okay, that we don't want to carry around for no reason, okay? And with that in mind, right, let's start labeling our degrees of freedom, right? So we go to node 1, nothing can move or rotate, so we skip, right? We go to node 2, right? And then at node 2, right, we said there's no horizontal displacement, so the first degree of freedom becomes the vertical displacement. I'm going to call it U1. there'll be an associated applied force. I'm going to call P1. Okay. And then this guy can rotate. Okay. So the slope that develops here, I'm going to call U2, right? And the corresponding moment, I'm going to call P2. All right. Okay. So if we go to node 3, this one cannot move horizontally. Okay. It can rotate, so it's natural to label the rotation here by U3 and P3. Okay. Cannot move up and down because of the rolling support. And node 4 doesn't move at all, or neither can it build up rotation. Okay. So as a result, we're done with labeling the 3 degrees of freedom. Okay. So let's label the rest. Okay. So you get U4, P4. Right. Again, as I said, we're going to discard horizontal displacement degrees of freedom from the 3 degrees of freedom, right? We're just going to put them in the prescribed DOF vector. So this becomes U4, P4. The horizontal forces become U5, P5, and the moments become U6, P6 here. Okay. Then U7, P7. Okay. U8, P8, vertical, U9, P9. Okay. And then here we have U10, displacement force, U11, P11, vertical, and then the rotation and moment becomes U12 and P12. Okay. Good. Okay. Right. So from there, summarize. UF is U1, U2, U3, right? So we have a 3 degrees of freedom that we're going to be solving for. And then UD, the restrained guy, is everything else. U4, U5, U6, U7, U8, U9, U10, U11, and U12. Okay, and this identically equals to 0, so won't really participate in the analysis. Okay, so now that we've labeled our degrees of freedom, okay, let's label our elements A, B, and C. Okay, and let's assemble, right, the structure stiffness matrix. So let's start with element A. And of course, natural orientation is left to right for each one of those guys, right? So node I is 1. Right? Left node is node 1. The rightmost node, okay, or node J, is node 2. Okay. Delta x equals L, delta y equals to 0. Okay, so L equals delta x. Right? This is the length. L is L. Okay. Cosine trivially becomes delta x over L equals 1. Sine trivially becomes delta y over L, identically 0. Okay. Implication is that gamma ROT is identity, okay, 6 by 6 in this case, right? And then local and global systems coincide. Okay. So we don't have to worry about the rotation matrix. Okay, good. All right, so then what about the K, right, for element A? Right, it's gamma ROT. For A, gamma RBM transpose, right? Also for element A. Note that the RBM gamma was the same for all elements in the case of the truss. Right? In our case, gamma RBM depends on the length. Okay? There are entries in that matrix that are proportional to the length inverse, and so it will depend on the element. Okay? Very important. RBM, so let me put this as a note here. Gamma RBM now depends on element geometry. Specifically, the element length. Okay? Right. Then you get the basic stiffness, K prime over bar A, and then you have the RBM for A, and then you have the ROT. Okay? We derived it a long time ago, and this is again holds for the beam column element. Okay? So now this is identity, as we decided. This is identity. Okay, so we're not even going to consider it. So the only thing that remains is this one. Okay, and if you look at the notes and listen to the previous lecture, we actually derived an explicit expression for this guy. Okay. All right. So then we can express this matrix. Right. This is our 6 by 6 guy. Okay. Okay. I'm not going to write the whole thing. Right. But what do we do first? We'll put the ID array. Right. So what is the ID array? Right. Well, let's go back to this picture. Right. And we see that locally, right, the first 3 degrees of freedom, right, point to 4, 5, and 6, right, and these are all identically prescribed, right. So the ID array entries corresponding to those are 0, okay, right, and then horizontal displacement locally points to U7, but it's 0, okay, because of the way we set up the problem, so there's no DOF there, right? So local U5 will point in the direction of U1, right? So U1 and U5 are the same. Delta 5 is U1, right? And then delta 6, which is a rotation at node 2, okay, becomes U2. So the ID array for this element becomes what? 0, 0, 0, 0, 1, and 2, like this. Okay. Likewise, we record this information on the left side, 1, 2, okay, which means that we only care about this part of the matrix here, 2 by 2. Okay. So if you look at the expression from the previous lecture, you get 1, 1, right? The 5, 5 entry becomes 12 EI over E cubed, or 12 EI over L cubed, right? Minus 6 EI over L squared, minus 6 EI over L squared, and we get EI over L here. EI over L, 4 EI over L. Okay. Right. And so now if we look at the entries of the ID array, right, this guy goes into KFF11, right? This guy goes into KFF12, right? This guy goes into KFF21, and this guy goes into KFF22. Okay. So keep that in mind. We move on to element B. Okay. Right. And so then much of the same happens. Right. Node I is node 2. Node J is node 3. Right. Delta X equals to L, delta Y equals to 0, right? From here we conclude just as before, cosine equals 1, sine equals 0, right? And then the gamma ROT equals identity, so we're gonna disregard it completely, okay? All right. Then, given the prior expressions, we can write K element B, right, equals to So we have a 6 by 6 matrix again, right? Okay, and then we need to go and write the ID array first. Okay. All right. So if we look at the picture for our problem, right? We're focusing on this element here, right? And so delta 1 points to U7, okay, so nothing. Delta 2 points to U1. Delta 3 points to U2, right? Delta 4 points to nothing. Delta 5 points to nothing. And delta 6 points to U3, okay? So the ID array becomes, for this element, 0, 1, 2, 0, 0, 3. Likewise here, 0, 1, 2, 0, 0, 3. Okay, what this means, I'm interested in this entry here, this entry here, this entry here, this entry here, right? All the interaction of non-zero entries of the ID array, right? This entry here, this entry there, okay? And this entry here, this entry here, and this entry here. So from the entire 6 by 6 matrix, I'm interested in the following 9 entries, okay? And if you focus on these 9 entries, right, this goes to KFF11, okay? And if you look at that entry, it is 12 EI over L cubed, okay? This would go to KFF12, right? And the entry here is 6 EI over L squared. Okay, let me maybe pick another one. Okay, let's pick this guy here. It goes into the location, what, 3, 2, right? 3, 2, and the entry there is 2 EI over L. Okay, and then the last guy goes into KFF 3, 3, okay, and then the entry is 4 EI over L. Okay. So to be sure, K32 is not 2 EI over L. Okay, what's 2 EI over L is the contribution to K32. Okay, plus, 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 and plus. Okay, so whatever is already in KFF, you just add the contribution there. Okay. Right, so finally, and I'll be very quick here, element C. Okay. Same story. We need to look at the figure again. All right, it's right here. No degrees of freedom at this node. Okay, 3 degrees of freedom. And only one free degree of freedom at this node, which is the rotation. Okay, and it points to U3. So for element C, KC becomes 6 by 6 matrix. Okay, but if you write the ID array down, okay, you get only one non-zero entry. Okay, 0, 0, 3, 0, 0, 0. Okay, likewise you put the ID 0, 0, 3, 0, 0, 0. Okay, so the only entry that's of interest is a 3, 3 entry, and if you look at the expression for the stiffness matrix, you find that this is 4 EI over L. Okay, and 4 EI over L goes with a plus to KFF 3, 3. Okay, so this should conclude the assembly procedure, right? And so what we find is our 3 by 3 structure stiffness matrix. KFF becomes 24 EI over L cubed. Nothing here. Okay. 6 EI over L squared. Nothing here. 8 EI over L. 2 EI over L. squared 2 EI over L 8 EI over L, like that. Okay, so nice and symmetric. Okay, if we again look back at our problem setup, recall we're applying a force P, okay, in the vertical direction at node 2, looking at that picture, okay. This is exactly the negative, right, for P1. So PF equals 2, right? P1, P2, P3, okay? We're explicitly applying P1 in the direction of negative y with magnitude P, so you get minus P here, right? And we're not applying anything on the second or third degree of freedom. Implicitly, it means the corresponding generalized forces is 0. Okay? Right, so the problem we need to solve now, okay, is KFF times UF, okay, equals to PF, okay, where KFF is given by this 3 by 3 matrix, and PF is given by this 3 by 1 vector. Okay. So you can actually struggle a little bit, okay? And I'll welcome you to go through the notes, right? Especially what I'll do is I'll summarize the end result. If you look at page 427, okay, you're going to find that under these loading conditions, UF is KFF minus 1 times PF becomes the following. Minus 5 L cubed P over 96 EI minus L squared P over 96 EI, okay, and then L squared P over 24. EI. Okay. So this becomes our vertical displacement, right? And these two are the rotations, okay, based on the labeling of the degrees of freedom. Okay. All right. So next, what would the element state determination look like? Okay. Okay. And again, conceptually, everything stays the same. Okay. It's just you need to expand everything to include forces and moments, right? And then displacements and rotations. So we'll go element by element. Okay? And first, you take the first element. Okay? And from there, using the idea array, right, which, if you recall, is 0, 0, 0, 0, 1, 2. Okay? Right? We find that we take, right, the entries 1 and 2 of this vector, and then put them in positions 5 and 6, right? We get 0, 0, 0, 0, okay, minus 5 L cubed P over 96 EI, and in the last entry, minus L squared P over 96 EI. Okay. Next is right, right? We need to find the forces. Remember F prime. Right? This guy is the same as kappa prime. There are no distributed loads, so the only nodal forces that will come from displacements, okay, times delta prime A, okay? And then remember delta prime A in this case is the same as delta A because gamma ROT, right, exactly equals to 0, okay? So you can actually make a calculation and find that F prime A equals 2. Okay? First slot is 0. Second slot is 9/16 P. Third slot is 7/24 PL, right? There's a moment. Okay. Third slot is 0. Fourth slot is minus 9/16 P. Okay. And last slot is 13/48 PL. Okay. All right. So these are the two x, y forces and moment, right, above the line acting at node I, right, and then below the line is two forces and a moment acting at node J. As expected, no action in the x direction produces zero force in the x direction. Okay, so what do we know here, right? So we can actually go and plot these quantities. Okay, so if this is our element A, right, we find that we have equal and opposite vertical forces. Okay, 9/16 P, 9/16 P. Okay, and then we have a moment of 7/24 PL acting like this, right? And then positive moment of 13/48 PL. Okay. All right. Let's we can repeat this procedure for element B. Right. Very similar. Okay. And what we find is a negative vertical force of 7/16 P, moment in a clockwise direction, so negative 13/48 PL. Okay. Equal and opposite force here, 7/16 P. Okay. And then another clockwise moment of PL/6 acting in this direction here. Mm-hmm. Right. Finally, going through element C, okay, we find positive and upward force, P/4, negative, P/4, okay, and then a moment of the acting in the counterclockwise direction of PL/6, and here counterclockwise PL/12. Okay. And so next, I suggest we put everything together. Okay. Right. So we're going to draw the structure. we have 3 elements. Okay, and so let's look at the forces first. Okay, so because there's no internal loads, right? Remember from our differential equation analysis, the vertical forces are constant on the element. Okay, and so clearly we have a vertical force of 9/16, right? And left node pointing up, right node pointing down is by convention a positive shear, right? So we can draw this plus, right, 9/16 p. Okay. Now, going to the second element, okay, we can see that the picture reverses, right? The shear changes sign and magnitude, becomes 7/16 p and negative. Okay. Going into the next element C, another reversal occurs. Okay, we'll go to positive p over 4. This puts us somewhere here. Plus p over 4. Okay, and so this is a shear force diagram for the whole structure. Okay, so we're gonna go to the moments next. Okay. Okay. And let's focus on element A first. Okay. Let me draw the moments down below. Okay. So we have okay, element A, right? We have a moment clockwise of 7 over 24 PL acting here, right? Okay. And we have another moment acting clockwise, sorry, counterclockwise of 13 over 48. So both moments are counterclockwise. 13 over 48 PL. Okay. So now what do you see here, right? So the moment acting counterclockwise, right, wants to create locally, right, wants to create a convexity, right, in the response. So the bar will bend this way. Okay. Counterclockwise moment at that node, right, wants to produce a response where the bar changes curvature, right, becomes like this. Okay. So the way to understand this, right, if you actually draw the distribution of the moment, and remember, vertical forces were constant, right, moments were linear in the absence of distributed loading. Right? So then what happens here is you start, right, your moment distribution would look something like this, right, where you start with a negative moment of 7 over 24 PL, okay? Negative moment meaning, right, you're creating a locally concave structure. At some point you're going to cross a 0. This becomes the inflection point, okay? And then you go into a convex structure. And then the moment becomes maximum, okay? And is equal to plus 13 over 48 PL, right? So again, when it comes to distributions, minus means moment that makes the structure concave, plus means the moment that makes the structure convex, okay? All right, and so then you repeat for elements B and C, right? And what you find when you put them all together, okay, in the first element, you go from minus 724 PL, right? That makes it concave, right? To plus 13 over 48 PL, okay, makes it concave, right? Then you start out right there, moment is continuous, okay? And then you drop down to PL over 6, right? So again, somewhere in the middle of the element, you're going to have an inflection point, right? This is concave, sorry, this is convex. Now you cross into the concave territory. This guy becomes minus PL over 6, okay? And then again, you go from minus PL over 6 to PL over 12 at the end, right? And so here you're still concave, right? And then you end up on the convex node. So now you have how many? You have one inflection point. You have another inflection point. And then you have another inflection point, right? Points where you change curvature, okay? So if you were to draw, right? If you were to draw the deflected shape, okay, let's try to do that now. You're cantilevered here, right? You're cantilevered here, right? You start out with negative curvature. Okay, you go up to about there, right? Then, at some point you change the curvature at the inflection point, right? And then you go up to the next inflection point with that curvature. Oh, apologize. Let's draw this again. All right, start out like this. Okay, you go here. All right. Then at some point you need to pass through 0. Okay, which would be that node here. Okay, you change the curvature again, okay, to concave, and then somewhere at this point you again become convex, right? Like this, you come in, right? So you have these sort of, so that becomes your deflected shape, okay? Okay, here you have a rolling support, so you have to be at 0. Okay, all right. So I suggest you go through that example again, okay, maybe on your own. Try to pick up on some of the details, and the next lecture will introduce some geometry. Okay, and try to set up another example where the rotation matrices are playing a role. Okay, let me stop here.